Hi, welcome to the fourth lecture about the financial math for actuarial science. This lecture is mostly going to be focused on bond valuation, and it does cover chapter 4 of the main textbook here, The Mathematics of Investment and Credit, 6th edition by Samuel Broverman, though I do often use ideas from the Theory of Interest, 2nd edition by Stephen Kellison. When you get into bond valuation, it's very important that you also be able to use the financial functions on your calculator. Here I have an old 15-year-old TI BA2 Plus that's got financial functions that can, for example, find yield rates for bonds. That's the big thing that you need it for. You want to make sure you have some kind of calculator like this, though I'm sure it would be fancier looking than this by now. We are in 2017. Before we get into the math content here, it's actually December 15th, 2017, and last night, December 14th, I went to see The Last Jedi. Yes, I am a Star Wars fan ever since my dad took me when I was a kid myself to the 1977 original Star Wars. Give you a 30-second review of The Last Jedi. There's the poster for it. What can I say about it? Well, it was kind of a wild and crazy ride, very much unexpected, as many people have been saying. Many people have been saying it went too long. I actually thought it was too short because, for example, I would have liked to have seen Rey and Luke have more time together to actually have some training. There really wasn't much training going on. It would have been nice to have a bit more training with that, but it was a wild ride. I'm not sure that I like all the directions that the director went with the characters, but we'll see what happens in episode 9. All right, on to math. And what I'd like to do in these lectures as well is I do like to tie up loose ends from the preceding lectures. So I'm going to talk some about lecture 3 here, which was about loans. You're probably going to want to watch that if you're going to make any sense out of what I'm about to say. If you want to just get on to bonds and you don't want to review loans, go ahead. I will probably put a time stamp to when I first start talking about bonds on the video here. But let's tie up some loose ends from lecture 3 about loans. We got a loan, L. And I'm going to assume the usual case here and for the purposes of review. We're going to assume we paid off with constant payments at the end of n periods, typically monthly, with effective periodic interest rate I. That would typically be a monthly interest rate. What are some formulas that are worth remembering about loans? Well, there's this formula for the payment amount. K is the symbol for the payment amount. It's L, the loan amount, divided by your present value of an annuity immediate with payments of 1. This equation is pretty basic, and it's derived by thinking about a timeline like usual. You've got your payments of K that are occurring at the end of each period, perhaps the end of each month, and the present value of all these payments needs to equal the loan amount. So L needs to be K times AN at monthly interest rate I. You can then solve this for K by dividing both sides by AN to get this formula. Then these other equations can come from the formula for AN. You know, AN is 1 minus V to the N over I, so if we're dividing by N, we can think of it as I divided by 1 minus V to the N. And V is the same as 1 plus I to the negative 1, so you can also write the equation this way. That's something worth remembering. You can certainly rederive it whenever you might need it, but it might be something worth remembering. Formula for the outstanding balance. At any moment in time, you can think of it either prospectively or retrospectively. I talked about that in lecture 3. This formula here is based on the actually the prospective method, where you're thinking about the balance of the loan at time t, where t is really going to be a whole number here, right after a payment, to be the present value of future payments. Okay, so K times this thing is going to be the present value of an annuity immediate for those future payments, n minus t of those future payments. And then you can write this in various ways. You can use the formula for K up here, substitute it in for K there, the i's end up canceling, and you can simplify it to this. And because, once again, V is 1 plus I to the negative 1, you can also write it like that. When you pay back the loan, you can think in terms of principal reduction. You've got a certain loan balance, it goes down over time. Typically, you pay not just interest, but you also try to reduce your principal. I won't explain this, but this is the formula for the principal reduction at payment t, time t. Again, if you go back to the last video and watch that, and especially focus on when I talk about spreadsheets, and what the general term of a general row of a spreadsheet looks like, you can see that formula derived, or at least discussed. Interest paid, you can think of it this way as well. Again, that's going to have more meaning for you if you go back and watch that video. But what I want to emphasize now is that you should, like in the last video, be able to and interested in thinking about such equations qualitatively in terms of graphs and their interpretation. And once again, I want to go to this program called Mathematica to look at how to think about these qualitatively. If you don't have Mathematica, that's fine. I'm sure there's some software out there that will do similar things. I'm just familiar with Mathematica. It is a fairly costly thing unless you have a student license. What I'm going to do here is I'm going to think about the graph for a loan with level payments. The graph of those payments as functions really of three variables: the loan amount L, the monthly interest rate I, and the number of payments N. And here, ultimately, what I'm going to plot is I'm going to plot this as a function of I, but then for different values of L and N. Mathematica allows me to do that. Will we see anything surprising? Does it make sense? Well, here's the graph that we get. Let me make this a bit smaller. So I've got the values of L, the value of L set to 20,000, the value of N set to 12. So this would be 12 monthly payments, say over a year. You're paying back maybe a car loan over a year. And I've got the payment amount per month, K, and there's going to be 12 of those payments as a function of the interest rate I. Now, I goes out to 0.5, a 50% interest rate, which would be really high. You would never want to have a 50% interest rate that you're paying. More typical rates would be between 0 and 10%. So typical monthly payments in this kind of situation, you can see by the scale here, would be between $1,000 and $2,000. But you do see, as you would expect, as the interest rate goes up, this function does increase. Your payments would go up. And it goes up in a nonlinear way. You can see it's slightly concave up. Though, something interesting and perhaps unexpected about this is the concavity seems to be mostly focused over here. Over here it looks almost straight, doesn't it? I can change L and N and see if that still seems to be the case. It's still, if you look at that, I think it still does kind of seem to be the case that at first it curves more than it does when I is larger. How about if N changes? Yeah, it still seems to be somewhat the case. Most of the curvature is for low values of i's. Can that be explained in any way? How about looking at the derivative of this thing with respect to I? That should tell us information, but that's kind of complicated. Mathematica did the differentiation there with respect to I with this input here. And you can see it's a really complicated thing. What's the limit of that as I goes to infinity or as I goes to 0? Can I give meaning to that? The limit as I goes to infinity is L. Interesting. This does have a limit. This derivative does has a limit as I goes to infinity, and it's a constant limit if L is fixed. It would be approaching a straight line with the slope of L. How about as I goes to 0? Does that have a limit for the derivative? Yes, it's a bit more complicated, but it does have a limit. Though that limit does depend on N as well, not just L. Can we see that here? Is the slope there seemingly equal to L? I don't know that I want to take the time to actually try to figure it out in my head mentally. But how would you do it if you thought about calculating rise over run here from this point there, say, to this point there? Calculate rise over run is close to 20,000. Okay? I'm going to go ahead and say it probably will be. It should be without actually calculating. Here I'm also making a graph of K as a function of N, the number of payments. As the number of payments goes up, as the term goes up from, say, a year to 2 years to 3 years to 4 years, up to, I guess that would be, 6 years at 72 months, your monthly payment does go down, as you would expect. If you've got more time to pay off the loan, then your monthly payment would be lower. This is, of course, a decreasing function, and it's concave up. Even though it's a discrete plot, you can see visually it's got a concave up kind of nature to it, which it would have to. I mean, you can't have a payment of 0. As the interest rate goes up, all these points go up.
As the loan goes up, they all go up, although the way they go up is different. Kind of interesting. As I increases, they're kind of all going up about the same rate, almost like a vertical translation. And as L goes up, the lower values of N cause larger increases in K as L increases than the higher values of N do. I don't know if that makes sense to you intuitively or not, but it's certainly something that would be worthwhile to look into. And you can calculate the limit of this as N goes to infinity. Does it have a limiting value? I times L is the limiting value of this function as N goes to infinity. It's not 0. I times L, I guess, would be the lowest monthly payment you could have. Essentially, if N is really, really humongous, it's like you're paying it off forever. Effectively, you're only paying interest. I guess that makes sense. I do have some other things here for the outstanding balance as a function of time. Let's just look at this quick. I don't think I'll enter all of this code here. We got a loan starting with amount L to be 20,000 again. You can think of it as a car loan, and is starting at 36, so that would be a 3-year payoff period. I is starting really low at close to 0. And basically the graph that you're paying off over 36 months here is straight. You're paying hardly any interest. If I increase I, you're going to pay a lot of interest perhaps. And yeah, that's a situation where you'd be paying a lot of interest, especially at first. This balance is barely going down over time because so much of your monthly payment is going toward interest. At the end, it goes down faster because a lot more now at the end is going toward principal. If you increase N, then the graph moves to the right. If you increase L, the graph moves up. Okay, again, all those things should make sense. When the interest rate is high and N is high, you really pay a ton of interest. You might pay more interest than the original loan amount when I and N are both really high. And that often happens with home loans, mortgages, especially because N is so high. I think I'll skip the rest of these things for the sake of time. I am trying to keep these videos to around an hour, but Mathematica is a tool that you can use to do this kind of graphical analysis to think qualitatively about these things. Okay? Not just thinking in terms of equations, though that is the main thing you do with problem solving for actuarial exams, but thinking about graphs. Now, you may not have Mathematica. Again, maybe you've got some other technology. Certainly there's open source stuff out there that you could use. But maybe you just want to play around with your calculator too and think about these things that I just showed you. There are more loose ends I want to talk about. I want to talk about, as I often do, an oddball example. Okay, why? Well, it's just because I enjoy it. It's not necessarily practical, though sometimes it can be practical. Excuse me while I get a drink of water here. Technology can help you deal with oddball examples such as strange continuous payment streams. Imagine you got a loan of $100,000 and you're paying it off in 10 years, and I guess these would be annual payments with force of interest equal to, say, 0.1. Let's do an odd payment stream. How about, and by payment stream, I'm meaning continuous payment stream, like you're paying money every second of every day, every millisecond of every day. Of course, if it's milliseconds, you're paying fractions of a cent. What if your payment stream is this kind of function, a trigonometric function, 1,000 cosine of 2 pi t plus some unspecified constant b. The graph of such a function k sub t is a function of t would look about like this. The period would be 1 year, so this would be 1 year where you're back to the maximum. And the average value of the function would be at b. Okay, so imagine you're paying back a loan every second of every day with a payment stream that oscillates in terms of how fast the money is paying off the loan. This is in dollars per year at any instant in time. T equals, for example, 0.326 or something. into a given year, you're paying, the money is flowing and paying out that loan at a certain rate. Okay, let's just pretend this is 10,000 or something right there. At that instant in time, the rate at which money is flowing into paying off the loan would be $10,000 per year. But the rate is changing. So sometimes it's flowing faster than others. Okay? You know, who would ever do this? Well, not many people. But I like thinking about it for fun because I just enjoy this kind of thing. But B can't be anything. You've got to choose B so that you pay it off after 10 years. And that means choosing B so that this equation is true. The present value of the loan amount, the 100,000, has to equal this integral. What is this integral representing? This integral is representing the present value of the payment stream. If I integrated without the e to the negative delta s there, that would be the total nominal amount of money that's paid when you integrate a payment stream like this. Without multiplying it by a discount factor, you are finding the total amount paid. Because for any little chunk of time, imagine s representing time here, ks times ds, times with quotes around it because it's not literally what's going on with the integral. If you imagine that as a multiplication, would give you the small amount of money paid during that small amount of time, ds, starting at time s. If I multiply by e to the negative delta s, where delta is the force of interest, that's discounting it back to time 0. So this would be a present value of that tiny amount of money. Integrating is analogous to adding. It's like you're adding up all those present values to get the total present value, and you want it to equal 100,000. Based on the nature of this payment stream, we can choose B so that this is true. You can use technology, or even you could solve it to obtain this for B. You should check this on your own. This integral is not too hard to do. You need a little bit of, well, you can either use a table or technology, or you can use integration by parts. It would be a bit painful with the 2 pi's in there and the negative 0.1s in there. But it's not impossible to do. Certainly you could try it by hand with calculator help and probably do it within 10 minutes. B needs to be 15,794.44 to make this paid off by time 10. So that's got to be the value to B here, the midline, the average value of this payment stream over 10 years to make that happen. Anyway, then you can use technology to maybe find the outstanding balance as a function of time in this case. And actually you can think about this with differential equations too. Now I talk about this a little bit at the end of lecture 3. I talked about some graphs. I don't really want to explain this at the moment. Well, I guess it makes some sense. If you think about the balance, you've got a balance on the loan at any moment in time. What's its rate of change going to be? Well, you know, you are owing interest at force of interest delta. So this term here does represent the rate at which interest is accruing, so to speak. It's proportional to the balance at any moment in time. But then you're subtracting off the rate at which money is being paid off, the loan is being paid off from the payment stream, KT. So this does make pretty good sense, I think. If you know a little bit about differential equations, you can, well, substitute into the function. Then you can use the method of integrating factors. With this as the integrating factor, and this is the initial condition to ultimately solve this differential equation. Now, if you don't know anything about differential equations, it's okay. Okay, you can skip this part. I'm only going to briefly talk about it here and look at the graphs. We will soon be on to bonds. But if you do know about differential equations and integrating factors, you might want to try this on your own. You can obtain this solution, though it's really messy. I had Mathematica simplify this for me. But it is possible to do. But yes, it's not so pleasant to look at. That would be the equation for the outstanding balance as a function of time. Does it look like a typical kind of outstanding balance graph? Yeah, from the long view it kind of does. Outstanding balance starts at 100,000. You're paying it off by 10 years, again with this continuous payment stream. But if you look at it a little closer, maybe you can zoom in there, it does appear to be a little bit wobbly. I guess that makes sense since the payment stream is wobbly. And in fact, we can zoom in a bit closer. You can see those wiggles a bit better. Okay, so sometimes the balance is going down faster than other times because your payment stream itself is oscillating.
Okay? So, not that you would necessarily be thinking about this ever in the context of actuarial exams or on the job, but if you're like me and you just enjoy thinking about these kinds of things, I hope that inspired you to consider more situations like this. All right, now on to our main content, bonds. What's a bond? Oh boy, zoom in on that. It's even hard for me to see though, I can't really read this. I do see the United States of America, $1,000. This is a picture of a $1,000 face value, hey, Lincoln's face, or par value bond. What is a bond? It's an issue of indebtedness of a borrower, not an borrower, a borrower, usually a government entity or a corporation, though it can sometimes be nonprofits too, like a church or a school will sometimes issue bonds. They are the borrower. They are borrowing money from a lender. The lender is, unlike the typical case when the lender is maybe a bank, the lender is you or somebody else. That's often individuals. Formally, they are called the bondholder. And so they are loaning money to the government or corporation or nonprofit, and they want to get paid back with interest, as you usually do with investments. Why would you do anything else? The interest often comes in two forms: periodic payments of interest, mostly at least, called coupons, and two, the redemption value at the end of the term that often equals this face or par value, for in this case would be 1,000, but rarely equals the purchase price, the loan amount that you loaned to them. It rarely equals that. That might seem a little strange. Why wouldn't you get a redemption value equal to how much you loaned out to begin with? Well, that's just the way it works, as we will see. There's a lot, now we're about to get into details, and in these details there's a lot of letters, variables, there's a lot of terminology, there's a lot of equations, okay? It's going to feel maybe overwhelming, especially if you haven't seen it before. I guess for my students I would recommend trying to read chapter 4 in this book to see all this stuff. If you happen to have this book, you can look at chapter 7 of that book. And so it's going to feel pretty fast if you've never seen this stuff before, and it's going to be hard to remember right away. But so you have to start working on problems too. And I've got a whole bunch of problem-solving videos. Again, I'll put a link to that on bond valuation that you can get into the details about this. I will consider some numerical examples, but it's going to be a lot of variables, terms, and equations. And so prepare yourself here. First, bond symbolism and terminology. P represents the price, okay? How much do you buy the bond for? F is the par value or face amount. In the example from the previous slide, that was $1,000. Just what is printed on the bond, if it does have a print form to it, or electronically, that face amount or par value is communicated. C represents the redemption value, okay? This is pretty standard terminology and letters to use. That's how much you receive at the end of the term of the bond. R is the coupon rate per coupon period, standard. Often that's a semi-annual rate, an effective semi-annual rate. However, be careful, in problems, it's initially quoted to typically as a nominal annual rate. To convert that to an effective semi-annual rate, you have to divide it by 2. Very common thing to happen in problems. J is the yield rate, essentially the rate of return on the bond per coupon period, often semi-annual. Sometimes it's called I, okay? Broverman uses the letter J, Kellison uses the letter I. Seems like most of the actuarial agencies in America at least want you to use Broverman, or that's what they encourage. And so J may be the more typical thing to use. Little g is called the modified coupon rate. per coupon period, often semi-annual. It is defined so that C times G equals F times R. These both represent the amount of the coupon, these periodic payments before the redemption value. Oftentimes C and F are equal, so oftentimes little g and little r are equal. But not always. Sometimes the redemption value C is different than F. To allow for that possibility, though it might be rare, we also consider a modified coupon rate. So if this equation is true, therefore you can also solve for little g, of course, by dividing both sides by C. N is the number of coupon payment periods. Often, coupons are paid semi-annually. Often you're told the term in years, 20 years for example. You need to double that to find then the number of coupon payments periods, oftentimes. 2 times 20 would be 40. K is the present value, the redemption value C at the periodic yield rate. J, I didn't write an equation for K, but think about that briefly. That would be C times V to the N, V sub J to the N if you prefer, where V is the discount factor. At yield rate J, V sub J would be 1 over 1 plus J. K is not the same as a payment on a loan here. It is the present value of the redemption value, C. And then there's something capital G called the base amount, which is not really related to little g, the modified coupon rate. It's defined so that G times the effective periodic yield rate equals F, the face amount, times the effective periodic coupon rate. These are, again, the amount of the coupons. G is kind of a funny thing to define, but it is useful in something called the base amount formula, so it's worth considering. Okay, so that's all the symbols and the main terms. How about some formulas? The most straightforward formula, the one that you should either memorize or be able to figure out pretty quickly by thinking about a timeline if you have to, right away, is called the basic formula, basic pricing formula. It would be the present value of all the coupons, thought of in the usual way. So let's look at this picture. We can draw a timeline. N payment periods. If N is the number of half years then, N over 2 would be the number of years. You got the coupon payments, F times R, that occur at time 1, 2, 3, 4, etc. And at the end, you also have the redemption value, C, at the end. We need to find the present value of all these things at time 0, so bring these back to time 0, discount them back in time. Present value, which is going to be the price at time 0. First of all, you've got the coupons that are all of amount F times R. Since it's an annuity immediate, you've got to multiply that by your annuity immediate symbol, ANJ. That would be, of course, with payments of 1 multiplied times F times R, and your payments are all F times R, plus K, C times Vj to the n. This is the same as K. And that is your basic formula. P equals frange. It's actually better if you use an I, fran E if it's an I. But it's nice to remember P equals frange plus CV to the n. Okay, is your formula. That's something it's worth memorizing, but though of course you can derive it pretty quickly by thinking about the timeline. Here it is on the screen in the form I wrote on the board, as well as in terms of J in a more detailed way based on the formula for AN here. And Vj, sometimes written more simply with a K in there. And it does turn out that you can also think about, basically with a prospective method, of the price at any moment in time at the given yield rate
by the same formula, and that's called the book value, just after a coupon is paid, with a very similar kind of formula. The only difference being that instead of N payments, you have N minus T payments. So this is essentially thinking about the present value of remaining payments at time N minus T, right after that last coupon payment at that time. You've got N minus T future payments left. So this is the present value of the annuity immediate from the coupons, and this is still the present value at time at time T of the redemption value at time N. It's called the book value at time T. Essentially, it's the same formula. And that is handy in some problems as well. There are other formulas. There's what you might call the big four formulas that we will get into here, which brings me back to my high school physics days when we talked about the big four formulas for motion. There's the next formula is called the premium/discount formula, or just premium discount formula. And that can be derived by making a certain substitution into the basic formula, replace V to the n with 1 minus j times an, which is something you should know, by the way. Where does this formula come from? It comes from the formula for an. The formula for an is this. That's something pretty much everybody should have memorized. Just solve that equation for v to the n. Multiply both sides by j, add v to the n to both sides, and subtract j an from both sides, and you will get the formula on the screen. If you make that substitution, you can rewrite the pricing formula in this way. Just think about it real quick here. Replace this v to the n right there with 1 minus j an, like that. Rearrange. C times 1 gets pulled in front here. FRAN and CJAN, minus CJAN, go together with a minus sign there. Okay, that's called the premium discount formula. And I will talk about benefits of the various formulas fairly soon, so hang on for that, though you may want to pause the video and think about benefits to this formula compared to the preceding formula. Perhaps one benefit might be if you happen to know an, and you don't want to bother finding v to the n, this would be a little bit quicker, but there are other benefits that are probably more important. There are even other ways of writing the premium discount formula. You could use either of these equations, which define little g and capital G, and make appropriate replacements. Though I will tell you that people don't typically think about these forms. I thought it was worth writing down here, just to emphasize that you could. Okay? Of these other forms, probably this one is the most common one to think about. When the bond is redeemable at par, when C equals F, which is often the case, thinking about it this way can be pretty handy as well. It allows you to think about P in relation to C, based on the sign of G minus J, whether it's positive or negative, is a little hint about its usefulness. This one and this one are the most common ways of thinking about it, but you could think about it in the other ways. There's something called Makeham's formula. You can use these three equations. FR equals CG, which again defines the modified coupon rate, little g. The formula for AN, and the symbol for the present value, the redemption value, K. Substitute into the basic formula to obtain this formula. Right there, that's called Makeham's formula. So we can see, yes, FR got replaced with C times G. AN got replaced with that. And this thing gets replaced with K. Do a little rearranging. Bring the J under the G. And then you could multiply the C through this thing here. Replace C v to the n with K. Rearrange. You can get this. That's a little exercise for you. That's called Makeham's formula. And the benefit of that, one benefit, is thinking about the relationship between G and J. Is G bigger than J or is G less than J? And how does that affect the relationship between P and C once again?
It's called Makeham's formula after somebody named Makeham, and there are actually lots of Makeham's formulas out there in actuarial math. This is just one of them in the context of bonds. But you could think of it as a premium discount formula as well. I haven't said what premium and discount mean yet, though. I'll say it real quick, though we'll come back to it. When you buy the bond at a premium, you are paying more than the redemption value. P is bigger than C. And when you buy the bond at a discount, P is going to be less than C. If, as the usual case, F equals C, so that little g equals little r, you can then write it in terms of F if you like, and little r as well. Okay? So again, we have this blizzard of symbols and terms. If this is all new to you, I'm sure it's feeling overwhelming. It takes time. You got to work on problems. Maybe you want to stop the video and work on problems before you come back to this and re-watch this part, starting with when I start talking about bonds. And one more formula called the base amount formula. We can use these two equations. This is the equation that defines the base amount, capital G. F times R, the coupon amount, equals capital G times the periodic yield rate. And AN. Make those replacements and obtain this equation here. In this equation, one quick benefit to see in it does have the benefit that you don't see any AN in it. So maybe this could be useful to solve for N, for example, because you don't see AN in there. If you happen to know V, C, and G, this equation would be relatively easy to solve for N as one possible application of this. N being, again, the number of coupon payments. Okay, you'd have to use logarithms, but that might be one benefit of this. Here's some general guidance, though. Most people default to the basic formula, and this is usually fine, okay? You can either memorize it and default to it, or, again, you can rethink about your timeline and present values. If you happen to just loathe memorization, you can rethink about it whenever you might need it, and that's usually fine. The premium discount formula is a little bit quicker to use than the basic formula, especially if the bond is redeemable at par, especially if C, the redemption value, equals F, the par value, face value. Again, because it doesn't have AN in it. Excuse me, it doesn't have V to the end, I meant to say. The base amount formula, like I just mentioned 30 seconds to a minute ago, is easier to solve for the unknown number of coupon payments N. It is also useful to help you see how quickly the price changes as N changes just by thinking about what happens to V to the N as N increases, for example. Makeham's formula and the base amount formula are relatively easy to solve for J. Let me write these equations up on the board here now. So there's the basic here. P equals FRANJ, frange or franny if you use I, plus C VJ to the N. There's your basic formula. There's the premium discount formula. P equals, let's see, it's C plus FR minus CJ ANJ. There is Makeham's formula. P equals K plus G over J times C minus K. And there is the base amount formula. This will be handy here in a few minutes as well when we use a spreadsheet, get more practice with the spreadsheet here. P equals G plus C minus G times Vj to the n. Makeham's formula and the base amount formula are relatively easy to solve for the yield rate. That's the same as 1 plus j to the negative n if you need the yield rate. If you happen to know, if it's not too hard to find, g, c, and n. Those are given to you. Or maybe you know v to the n and you can solve for j too that way. That would be real easy. But if you're thinking in terms of the basic formula, that's when you have to use calculator functions to solve for the yield rate. I'm not going to take the time to show you calculator functions in these lectures, but in the problem-solving videos I do have them. Again, if you want to zoom in on that close, your calculator should look something like this. Is that it's coming out? Can you see it okay? All right. You can use it to solve for j if you're thinking in terms of the basic formula. Both the premium and discount formula and Makeham's formula could be thought of as premium discount formulas to help you think about the relationship between the price P and the redemption value C. Again, come back to the board here. P, what's the relationship between P and C? Well, P is going to be bigger than C if, for example, FR is bigger than CJ. It'll be less than C if FR is less than CJ. P is bigger than C, that's called buying at a premium. P is less than C, it's called buying at a discount. Makeham's formula can be thought of that way as well in terms of the relationship between G and J, little g and little j. If this is bigger than 1, if little g is bigger than j, then this is going to be bigger than k plus c minus k, which is c. You buy it at a premium. If g is less than j, this is all going to be less than c. You're going to buy it at a discount. There's more detail about that. Just reminding you what I just said. When P is bigger than C, when the purchase price is bigger than the redemption value, you're effectively loaning more money than you're going to get at the end. You're buying at a premium. P is less than C, you're buying at a discount. You're loaning less money than you're going to get at the end. P equals C, it's bought at par, but that would rarely happen. And by the way, these prices are typically determined by whatever the going yield rates are for bonds of various terms. Okay, it's all market-based. Okay, so based on the bond market at any instant in time, giving you certain yield rates based on certain terms, that determines what J is and therefore determines the relationship between P and C ultimately. And again, those formulas help you think about these relationships. Okay, I'm about to show you how to think about these things with a spreadsheet too, and that'll be the last main thing that we do. When you buy a bond at a premium or at a discount, amortization of premium or accumulation of discount. Let's think a little bit more carefully about this. When P is bigger than C, when the purchase price is bigger than the redemption value, you are effectively loaning more money than you're going to get at the end. When is that going to happen? When are you going to buy at a premium? It's when FR is bigger than CJ. Again, from the premium discount formula, this is going to be a positive quantity then, so P is going to be bigger than C. What's happening there? Why do you end up paying more than you're going to get at the end? Well, FR being bigger than CJ, especially clearly in the case where F equals C, effectively means you've got relatively high coupons compared to the yield rate. Your yield rate's relatively low, your return's relatively low, your coupons are relatively high. You're loaning them a lot of money, and they sort of make up for it right away by giving you pretty high coupons, is the way I think about it intuitively. The coupon payments are going to be pretty high compared to the yield rate. They're going to cover more than the interest owed each period, each half year typically. Therefore, what you might call the outstanding balance on your loan to them, OBT, as in Lecture 3, or more commonly with Lecture 4 here, book value, BVT. These represent the same thing, the current balance at time t. Think of t as a whole number of periods here. That balance that you are owed goes down right after each coupon payment. the balance starts out higher than C because you are loaning them more than C. It's got to go down to get to C at the end so that they can pay it off at the end. It more than covers the interest that they owe. They are paying down their loan that you made to them, essentially. That's called amortization of premium, and it's called writing down the bond. On the flip side, when you buy the bond at a discount, when the price is less than the redemption value, P is less than C, FR is less than CJ. If, in the common case where F and C are equal, that would mean R is less than J. That means your coupon payments are relatively low compared to the yield rate, which again is like your rate of return. So they're not paying much interest. They're paying you less than they owe you each half year. The coupon payments do not cover the interest that they owe. J is large compared to R. Therefore, the balance that they owe you keeps going up. The initial balance was P, lower than C. It's going up to the value of C by the end. It goes up right after each coupon payment. And this is called the accumulation of discount, or writing up the bond. As far as using a spreadsheet now, to see what's going on here, it is helpful, as I've emphasized here, to view the bond as a loan from you to the government entity or corporation. Whereas in Lecture 3 and Chapter 3 in Broverman, we're talking about loans that you take out and you pay back. Now you are the loaner. They are borrowing from you. We can think about using a spreadsheet to see the outstanding balance, the book value, change over time. Let's go ahead and do that here. And once again, re-emphasize the meaning of spreadsheets. And I'm not sure, is it coming on okay here? Maybe I should turn off the light.
Yeah, that's good.
I probably should make this a little bigger. So what I'm going to do here is I'm going to emphasize a number of things. I'm going to re-emphasize the meaning of all the terms and the symbols and their relationships to each other. I'm going to re-emphasize the formulas right here. We're going to think about it with this amortization schedule that we're going to end up making in a similar way to what I did in Lecture 3. And we will see this amortization that can happen either with a premium or a discount. Okay, so let's review. We got the face value, F, also called the par value. I'm going to take that to be 1,000. The redemption amount, C, often equal to F, but just for sake of interest, I'm going to go ahead and do a case where it's not equal to F. I'm going to say we're going to get paid back 1,100 at the end. Again, the face value is not the purchase price. That's maybe a point of confusion for people. The face value is just the amount that it says it on the bond. You know, and if it says it on the bond, why would F and C be different? Okay, but evidently they sometimes are. So we're gonna, for the sake of interest, we're gonna make it different here. Again, in problems, usually these rates are quoted as nominal annual rates. So I could quote a nominal annual coupon rate and a nominal annual yield rate. 8.8% and 6.4% is what I picked here. But you're more interested in R and J, which, as in the usual case, at least in the United States, if the coupons are semi-annual, you want to think of these as effective semi-annual rates. You need to divide these other ones by 2. And I did use spreadsheet functions to do those calculations. Oh boy, here, this is pretty small. If you zoom in right there, might be difficult to see, got to zoom in pretty far. It says equals B3 divided by 2. Might be too difficult to see. I mean, it doesn't even look real clear to me, and I'm real close here. Equals B3 divided by 2. Come back over here now. In this cell, I typed, excuse me, I typed equals B3 divided by 2, meaning I took the number in cell B3, column B, row 3. Oh, you can't see the 3 over there. There's a 3 over there. And I divided it by 2, and the answer goes in cell B4. And the benefit of this is I can make changes to cell B3, like I can change this to a 10%, and watch B4 gets updated to 5%. Got it? I'll go back to 8.8%. When you use formulas, as I emphasized in the last video, things get updated correctly. I did something similar here. In this cell, which is cell B6, I typed equals B5 divided by 2, which sticks to 6.4, then and divides it by 2 to get 3.2. In this cell, I found the discount factor V, effective semi-annual discount factor, based on the effective semi-annual yield rate, J. Oh boy, and this looks really difficult to see here. I typed equals in parentheses 1 plus D6 to the negative 1 power, 1 plus J to the negative 1. J was being in cell B6. Boy, that's really hard to see, but trust me, it's there. Number of years, I picked to be 10. Here I doubled that to get the number of payments to be 20. I am assuming semi-annual payments. Here are the coupon payments. Let me go ahead and just retype the formula here, although I deleted it. You can see I took it from these two cells. The formula is F times R, so I can type equals B1 times B4 as the amount of the coupon. $44 in this case, 4.4% of 1,000. This is the modified coupon rate, little g. Turns out to be 4%. It's F times R divided by C. I took 44 in the cell and divided it by C in the cell. You can try that on your own. 44 divided by 1,100 is 0.044%. Notice the percent sign. I also calculated the base amount. Capital G is the coupon amount, FR, divided by J. So take 44 and divide by J, divide by 0.032. Try that on your own, you'll get 1375. Here I did the present value of annuity immediate. This is AN. I did 1 minus this thing to the n power, take 0.96899 to the 20th power, subtract it from 1, divide by 0.032. That's this number. You can check that on your own. That's AN. All right, let's go ahead and type some formulas now. Basic formula. I've got it on the board here too. Maybe I'll turn the light back on now. FRAN plus C times V to the N. Maybe I should have a spot for V to the N here. Let's go ahead and use it here. So I'm typing it now on the spreadsheet. F times R is in cell B11. You can see it got highlighted. Times AN, which is in cell B16. Sorry you can't see the numbers on the left. That's the present value of all the coupons. Plus C, the redemption value, which was in B2, up there, times V to the N, B7 to the B9 power, B7 to the B9 power. FR is B11, AN is B16, nothing right there. B2 is C. That's V, B7 to the N power, 20 power. Check this on your own. The price of the bond is $1,228.53. So it's being priced at a premium. That's bigger than the 1,100. Bigger than C. The amortization schedule is going to write down the bond. You are loaning more money to them at the start than you're going to get at the end. You are, in a sense, getting a loss, but they are paying you a lot in coupons to sort of make up for that. Let's check this with the other formulas as well. Just to confirm, we get the same thing, but you should try these on your own too. Premium discount formula, I'll go ahead and use that. C is in cell B2. Parentheses, I have F times R, which was in cell B11, minus C times J, B2 times, where was J? B2 is C, J was in cell B6, times AN, which is in cell B16. See it get highlighted there. This is the premium discount formula. It should give us the same answer. though it's using more decimal places. Tenths of a cent there. I could reformat that, but I won't bother. Let's try Makeham's formula next. Here it is again on the board. K plus G over J, this is a J here. G over J times in parentheses C minus K. Do I have a spot where I actually calculated K? I guess I did not put a spot for K here anywhere. I probably should have. K is C times V to the N, V2 times, again, V is in B7, N is in B9, that's K, plus G over J, little g is in cell B13, J was in cell, I forgot, B6, times, in parentheses, C and B2 minus K, once again, B2 times B7 to the B9. Hopefully this gives us the same thing, and it does. Hey, the decimals went back down again. I don't know how that happened. Wasn't even watching, and it happened magically. Finally, we use the base amount formula, confirm we get the same thing. Capital G is in cell B14, plus C minus G, again, C will be, okay, C is from B2, minus G, which was again in B14, times V to the N, B7 to the B9 power. Watch this again if that went too fast for you. Yep, we got the same thing, and now lots of decimals back there again. Okay? So I confirmed that all the formulas give you the same thing. You should try it with your calculator as well. We're going to getting pretty close to the end here. Now I want to go ahead and fill out this amortization table based on the loan amount, which is the price. At time 0, that's going to be called the book value, and it's just going to pull that price over into that cell. So there's the amount you purchased the bond for, that's the loan amount. The coupons were $44. I can pull that from cell B11. All right, here's something to be careful about though. I want those coupon payments to be constant at $44. I could just type 44, but I want to go ahead and pull from B11 just in case I wanted to make changes. However, I want that cell reference to say fixed as I copy and paste the formula down. And I need to use dollar signs to keep the cell reference fixed. Those dollar signs don't mean money. $B, $11 is one way to do it. Technically, I only need the second dollar sign in front of the 11. If I copy and paste downward, the column B will stay constant for sure. It's the 11 that you certainly need to stay fixed. And again, I'm sorry you don't see the 11. It is over here. It's row 11. But it doesn't hurt to put it in front of the B as well to keep the column fixed. Just as you're not sure which one it's going to be, you just want a quick and dirty thing. Put the dollar in front of the B and in front of the 11. That cell reference will stay fixed. As I copy and paste downward, it'll always be 44. When you don't use cell references that are fixed, as I will not in this next one, well, partially at least, then these cell references get updated. As you go down, the number will get updated to the next values. I'll show you here in just a second. What's the interest that you owe? It's based on the periodic yield rate and the balance. The periodic yield rate, J, this number, 3.2%. I better double check that. Yes, that is J. In cell B6, I do want that to stay constant as the periodic semi-annual yield rate. That is the interest rate for the loan, essentially. However, when I multiply it by the balance, is not going to stay fixed. For this first payment, it's going to come from the preceding book value in H4,
H4. However, I don't want to use dollar signs there because I want that to get updated to H5 when I copy and paste this formula to this next cell. One down, it will make the 4 change to a 5 based on the new balance after that first coupon payment. And that's what you want. Got more decimal places? I'm not going to worry about it here. Remember, when you buy the bond at a premium, that means the coupon, you're sort of made up for it by the coupon's payments being relatively high. They are paying more than the interest that they owe you, which you can see here. The difference, 44 minus 39.31, will be the principal repaid, the amount that the book value goes down. Calculate that difference like this, and do not use dollar signs because I want that to get updated, for example, the next cell to being equals E6 minus F6, and E7 minus F7, etc. That's how much principal is repaid with the first coupon payment. So your book value goes down by that amount, and I can type equals H4 minus G5 to find the new book value. It goes down by $4.69. And don't use dollar signs there because you want that to get updated, for example, in the next cell to equals H5 minus G6. This is ready to copy and paste down now, these formulas, which you can accomplish just by highlighting them all and clicking and dragging the lower right corner downward. And you can see, as I start to do this, that the interest owed each period goes down because the balance is going down. More is going toward reducing the principal. These are going down faster and faster. And by the end, we should get down to the redemption amount, which is $1,100. By the 20th payment here, we do get to $1,100, which was C, the redemption value, which they can now pay off with redemption at time 20. I can add another row where I have a 1,100 here, effectively 0 interest here, and copy and paste this, 1,100 paid off to bring your balance down to 0. The dash means 0 after they give you the redemption value at the end when they don't owe you any more money. The bond's term is done. We can calculate totals for these things. Built-in function equals sum, S-U-M, meaning add up things. The first number up here is in cell E5 down to E25. I can do E5 colon E25 to add those numbers up. And I can copy and paste that over in the next couple columns. I can just click and drag to see what these add up to, and it should make sense, hopefully. Come on, it's not dragging for me here. Oh, there we go. So notice that the sum of all the principal repaids, including the redemption value, is the loan amount. It's the purchase price, $1,228.53. Here's all the interest you paid. If you add these two numbers, you get that number. That's the total amount that was paid to you. This was the amount of interest they paid. Yeah. So this is definitely summarizing what happens. And again, the book value, the balance, when you buy at a premium, goes down to the redemption value at the end. And if you graph it, these go down faster and faster. If you graph it, it's a concave down graph. I'll talk about that some in the loose ends in lecture 5. If you buy the bond at a discount, if I now make the yield rate bigger than the coupon rate, I think I'll change the 6.4 to a 10%. That'll mean the price P will be less than the redemption value C. I'll make this a 10, watch everything change. J now becomes 0.05. The price is lower now. You're buying at a discount. These are less than 1,100, less than C. And the coupon payments are relatively low compared to the yield rate.
the book value, the balance that they owe you, because the coupons do not cover the interest owed based on the yield rate J, these need to go up. The principal repaids are really negatives, parentheses means negative. These numbers go up. Their balance that they owe you goes up over time because they're not paying the interest that they owe. But at the end, you are still back to the redemption value of 1,100, and they do pay it off. The 962.92, that's the same as the price. Here was the interest column, right? That's the total interest. Add these two things, and you get the total amount of all the money that you received, which in this case was the same as the last one because the coupons were the same. I kept R constant there. No, we didn't have to. If you graphed this BV as a function of time, you get a concave up graph. This graph was concave down. I shouldn't have used green. That's at a premium. Graphing the book values as a function of time. And really we've got discrete values here. I'm connecting the dots anyway, and this is bought at a discount. And in both cases, you end up at a value of C at the end. Okay, and you have the spreadsheet graph these for me if I wanted to, but I won't take the time for that. Almost done. I'm going to just briefly mention some other topics that you should know about for the actuarial exam, but I'm not going to really get into details. They are in the book, and you should practice some problems for them. I do some problem solving with these. I probably will talk about them a little bit in the loose ends for lecture 5. You could talk about reinvesting coupons. That's what investors often do. They get the coupons, payments for the bonds, and they reinvest them. So you might, for example, wonder what the total rate of return is overall. There's something called zero coupon bonds, which is exactly what it sounds like. Zero coupons, you don't get any coupons, you only get the redemption value at the end, and that's actually simpler than the case of coupons. There's something called callable bonds, which is a little tricky. Basically, the borrower could decide they want to give you the redemption value anytime they want. Okay? You're loaning the money, but they can pay you back anytime they want. And the basic idea of how to deal with problems related to callable bonds is you want to think worst case scenario for you. If you want to get a given minimum yield rate, think about the worst case scenario of when they might pay you back, and I'll let you think about that and read about that. And you can talk about valuation of bonds between coupon dates. The main thing you should know as of 2017 in terms of doing problems where you are evaluating between coupon dates is to use something called the semi-theoretical method to find the so-called marketplace price or clean price. There's a dirty or flat price that takes accrued coupons into account and is actually more related to the money that changes hands. There's something called the clean or market price, which is kind of a simpler concept. It ignores the accrued coupons, and you can use this formula here, the semi-theoretical method, to find the market price. And my notation is off here. This should be the book value at time t plus k, where k is a number between 0 and 1. The time is in periods here, so t would be in half years typically, and k is some fraction of a half year between 0 and 1. So for example, 3 months, k would be 1/2. 2 months, k would be 1/3. P0 is the book value at time t. I really probably shouldn't have used that notation, but I was going with what Broberman had here. You can use this formula. Finding k, you can find with various methods. You can figure it as actual number of days divided by total number of days during the coupon period, during the half year, as the fraction of a year. This is the way to find this market price, this clean price, ignoring the accrued coupon. It's got some funny things that go on with it, actually, and there is a problem-solving video that I did. right around video number 115 or 16 or something, where I looked at graphs of this thing based on the semi-theoretical method, and it's really quite weird what happens with it. But it is the standard thing to use as of 2017, so it's something that you should know for the exam. And the other methods, which are called the theoretical method and the practical method, are not used as of 2017 on exams, though they actually do make more sense. Okay, and they're even simpler, you might say. So those are the other topics that you should know for the exam. Went longer in this video. I hope you enjoyed it anyway in my brief Last Jedi review, and I wish you well in studying for the exam.